some logarithmic functions. What's neat about logarithmic functions is that they are actually the inverse to exponential functions. So last week we talked about exponential functions growing quickly or decaying quickly. And you can have an exponential that is growing at any rate. So we talked about things that were doubling. There's also this number e that's about 2.7. We talked about that. And so whatever rate that that's growing at, we need something to cancel that out in order to solve an exponential equation. So if you look at the graph of a logarithmic function with that same base as the exponential, there's a reflection across the line y equals x. So this exponential function is e, so when we reflect it, we get the log base e function, which is called the natural log. So that's kind of a neat tidbit, because once you get into solving exponential and logarithmic functions, you're going to use the other one to simplify. So just like when I'm doing solving an equation and I have addition and I want to get rid of it, I use subtraction. Or if I have a square root, I square it. Or if I have division, I use multiplication. When I have an exponential function, I use the logarithmic. Or if I have a logarithmic, I use the exponential. And so what you'll notice about the logarithmic function is that it grows quickly and then it kind of levels out. It has a lot that's kind of flip-flopped from the exponential function because exponentials take a while to get started, and then once they do, they grow very quickly. Logarithmics are increasing rapidly, and then they're kind of slowing down. You'll also notice that the exponential function, remember we had talked about it having a horizontal asymptote, but logarithmics have a vertical asymptote. We had talked about how the domain of an exponential function is all real numbers. That's not true for the logarithmic because of this asymptote. However, the range is all real numbers. So we're going to talk a little bit more about that. So I'm looking at just a parent function that's logarithmic. It could be any sort of base. The natural log ln x is a base with e, so you could write log base e or ln x. And then you also have logarithmic functions that have base like 2 or 3 or whatever. If you don't see a number, it is implied that it's 10. You can write the 10 there, but you don't have to. And you'll notice that I have that the vertical asymptote is at x equals 0. If we start shifting this function to the left or to the right, that will change. So let's look at the domain of this function. We are not touching the x-axis. We are starting just after it. There is an asymptote. So we're going to start just after 0, and then we're going to infinity. I'm using parentheses on 0 because 0 is not included. If I want to start right after 0, I use the parentheses to show that. So I don't want to start at 1 because I want to include values like 0.001 and even smaller values. My range for a logarithmic function will always be all real numbers, so negative infinity to infinity, or we can use the symbol all real numbers. Now my end behavior for these functions is a little bit different than the exponential function. So I'm focusing on my ends. Let's talk about the left end first, then we'll talk about the right end. So I'll label these over here. So I have the left end. When we're going to the left, x is not approaching negative infinity. It's not even going over that way. The farthest left that this function goes is to 0. That left end is pointing down, So it's going to negative infinity. The right end is going to the right. It's going to positive infinity. There we go. That's a little bit better. All right, not much. And then y, it's going up to infinity. This value will always match this value. So if you have a shift and you graph this, then if that's, if this is a 3, then this will be a 3. But this is what your end behavior should look like. Most of the values should be an infinity or a negative infinity, but one of them is actually going to be a number. That's a little bit different than if you're looking at a polynomial. Now, with our exponential functions, we were approaching a number, but that was on the y value. This is on the x value. So everything that you know about exponential functions is really kind of flip-flopped. Let's look at another one. So if you're looking at this logarithmic function, it has a base 3, and it has x minus 2. The 3 doesn't really do a whole lot. If you know your transformation rules, which it's okay if you don't, I'm going to show you how to use Desmos to figure this out. If you have subtraction within the function, that's going to move it to the right that much. So if my asymptote is normally at 0, I'm actually going to be to the right 2. And then I'm going to have that logarithmic shape. So my vertical asymptote is at x equals 2, which makes my domain 2 to infinity. My range is always all real numbers. So again, this is matching this value. So when we go to do our end behavior, my left side of the graph, the most far left of this graph that I see is 2. But what is that left end doing? It's pointing down. The right end is going to infinity, and it's pointing up. So I'm in Desmos, and I want to show you how to use this to answer questions about asymptotes, end behavior, domain, and range. Just in case if you don't know the transformation rules, which again is fine. So you can graph any log function in here. Now, if you just graph log x, that's going to be a base 10. If you graph ln x, that's going to automatically be that base e. If you want to graph a logarithmic function that has a different base than 10 or e, you will need to hit shift and then the dash, the key that is right next in between the 0 and the equal sign. So when we do a superscript, shift 6, that's what we used last week. Now to get the subscript, I am going to do shift and then the dash, so the key in between 0 and the equal. So let's say I have 3, and then the problem I had was x minus 2. So if I don't know those rules off the top of my head, or I just want to verify, or I want to, kind of discover, I can graph that in Desmos, and I can see that my vertical asymptote is 2, which again tells me that my domain is 2 to infinity. It also tells me what my ends are doing, that I'm approaching 2, that's the left side, and the left end is going down, and I can see what the right end is doing. You're also going to be doing some discovery in Desmos, or in Delta Math this week with your assignment. So I want to show you in Delta Math this week, you're really just using Desmos and you're discovering and kind of playing around, and then we're going to do some application. But when you go to the first few sections, you are going to be creating a table of values. So you're just going to be using Desmos and filling out this table. So if my x value is negative 15 over 16, you can just go to Desmos and type in negative 15 over 16 plus 1. Then you can come over here and use Desmos to do that value. So let's say I want to figure out what that second part of the column is. And I think it was log base 4. There it is, log base 4, x plus 1. And my x is negative 15 over 16th. So when I add 1 to that, that would be 1/16th. Because you would have already figured out that part. I need to add some parentheses. And so that value is negative 2. So when I go to Delta Math, I would have figured out what that value is, figure out what this value is, and then you just keep going and filling out that table. Once you fill out that entire table, you're going to see that graph. As you continue through this assignment, you will have different variations of problems that have been shifted up, down, left, right. Shifting the function up and down is not going to affect anything. It's really the left, right that's going to affect your domain. And then also we can flip it across the x-axis will affect some things as well. So you're going to kind of play around with that. And then you're also going to use Desmos to calculate what the, or figure out what the asymptote is. Again, that's what I showed you where you're just graphing that function. And then again, just like last week, you'll have a section where you're filling out all the bits and pieces about that function. The final thing that you're going to see on this assignment are some application problems. So for example, you might see something like this, where you have some sort of an equation and you're given the values and you're just going to plug those values into Desmos. So for example, this one is log base 10. There's an initial or an intensity value, which is 100. And there's a reference intensity, which is 1. I'm going to go to Desmos and type that in. So I went ahead and typed this in. I didn't type the base 10 because that's the default base. If you do type the base 10, it won't change anything. Oh, I was hitting Control instead of Shift. There we go. So you can see that that doesn't make a difference. So that's all you'll be doing on that last little section, is you will be given some sort of word problem with a formula, and you will be plugging this information in there and letting Desmos calculate it for you, just so that you can see a little bit of application. I'll go ahead and type this one in. So I went ahead and typed this one in. Whenever I did 3.2 times 10 to the negative third, I just put both of these pieces in parentheses, and then I grouped all of it in a larger set of parentheses. Now you could also use the keyboard down here for multiplication if you want to do that. So I could take these out and put in the multiplication symbol, and it would give me the same answer. I am going to have you round to the nearest tenth, which is 1 decimal place, so this one would be 2.5, but you're going to let Desmos do a lot of the work this week. I just want you to see some application and kind of play around and do a little bit of discovery and hopefully have some fun.